And welcome to the Tunneling Project Insights webinar with NASTT. My name is Carrie Webb and I work for NASTT, and it's my pleasure to get us kicked off for the day. During today's event, you all are in listen-only mode, so that means that we cannot interact with you verbally. So we do ask that you just submit all of your questions through the question box. Really quick reminder, make sure that everything else in the background is closed down just to optimize your video and audio. This includes Outlook, Teams, Ring Central, any other programs you might have running. This just makes sure that all the presenters come through clearly for you. But if you should have any tech issues, make sure to utilize that question box. I will be on the line to kind of assist with that the whole time. But with that, I will pass it off to Marty to get us started.
All right, thank you, Carrie. I also want to welcome everyone to our webinar today on Tunneling Project Insights. And Grace, if you want to go ahead and share your screen now. So certainly hope that each of you gained some new insights today, and I encourage you to take notes, because at the end we will have time to answer questions. So if you want to take any notes as we walk through our presentation today, we'd be glad to answer those at the end. And my name is Marty Paris. I'm one of the practice leaders here at Kimley-Horn. And today I've got with me 4 of my partners across the firm who are going to be sharing about different projects that they have worked on related to tunneling. And the one thing that we all have in common is that we all work closely with Matthew Wallen with Bennett Trenchless. And so Matthew is also going to be presenting today and helping us with this webinar. Our agenda for today is going to be a quick introduction to Kimley-Horn and Bennett Trenchless, and then Matthew Wallen will do an overview of some of the trenchless technology methods that we're going to be talking about today, most of which will be open face technologies. And then we're going to walk through 4 case studies, one from San Antonio, one from Fort Worth, one from Las Vegas, and one from Houston. And so we'll walk through those, and then we will enter into our time of question and answer. So for those who are not familiar with Kimley-Horn, Kimley-Horn is a multidiscipline consulting firm, national across the U.S. We now have over 9,500 employees and over 145 offices. And a big part of our practice is doing water and wastewater work. And of that practice, over half of it is related to pipeline work. And with that pipeline work, we do a lot of tunneling work. As you can see, we've actually literally done hundreds of miles of tunnels and other trenchless methods. And one of the things that, is as we worked on those, we worked closely with Bennett Trenchless. And so I'll let Matt talk a little bit about Bennett Trenchless.
Okay, thank you, Marty. Yes, as an introduction to our firm, Bennett Trenchless Engineers is a small 100% trenchless consulting design firm. So all we do is design, construction support, and claims assistance for new installation trenchless projects. So auger boring, open shield, pipe jacking, and tunneling methods that we're going to talk about today, microtunneling, HDD, so on and so forth. There's only 6 of us. We're a very small firm, but we do quite a bit of work around the country. And we've been doing this now for 28 years. The Bennett, Staley and Bennett Trenchless firms have existed and been doing this work continuously. And we've been fortunate enough for 20 of those 28 years to collaborate with Kimley-Horn. We've done over the years, I think, over 50 projects with Kimley-Horn, and really enjoyed this relationship and the projects that we get to work on with them and the team that they have. And so we're excited to be asked to be a part of this webinar and to present some of the projects that we've worked on together in the last few years. So with that introduction, I'm going to jump in before we get into the case studies. I'm just going to do a few slides to kind of introduce the ideas and some concepts and descriptions and applications for open face tunneling, open face trenchless methods. The 4 case studies we're going to show you today are all using variations on open face tunnel excavation methods. So we thought it would be prudent to just cover a little bit of background on that before we get going. So In the opening slide of this section, I'm just going to offer a description. Civil engineers, we may not be the most creative folks out there, so you may not be surprised to hear that open face tunneling is a tunneling method where the face, the tunneling face, is open to the ground. We are, those inside the tunnel are looking at the ground that's being excavated right in front of us. That material is being excavated, sometimes using hand tunneling methods or using mechanical methods right at the face, and then is typically loaded into haul carts or sometimes conveyor belts to be removed either just away from the face a little bit or moved all the way back to the shaft. You usually see haul carts moving most of the material back to the shaft, though on some projects you may see a conveyor system going all the way back to the launch location. We have people inside this tunnel, so that's a key aspect of this type of trenchless method as opposed to some things like auger boring or micro tunneling where there are not personnel inside the tunnel. In what we would call open face tunneling or open face pipe jacking, there are going to be people inside running the equipment that's excavating the ground or as I said, perhaps manually excavating the material. The guidance for these kinds of tunnels is typically a laser that projects the line and grade that's intended for the tunnel from the launch shaft out to the tunnel face so that the operators and folks can guide the tunnel and keep it on line and grade. You may sometimes see theodolite systems, especially lasers were very standard maybe 5 to 10 years ago. You're starting to see some more types of guidance that are more common, like I say, some theodolite and other optical type systems. And even in some complex installations where you might be turning curves and things, you might see gyroscope systems. But laser is still very common. And then the tunnel support that's being installed as the excavation phase is excavated and the tunnel is moved forward, we have to support the ground somewhere. So we'll talk a little bit about fixed liner systems where a segment of liner is erected in the tunnel and that segment never moves once it's established. And so the only thing moving is the excavation face or the shield at the front that's protecting the workers as the tunnels advance. That type of installation is typically referred to as conventional tunneling versus a moving type of liner, which is what we're doing in pipe jacking, where every stick of pipe that's added to the string is pushed forward and the entire liner is advancing until the tunnel is complete. All those consecutive jacking pipes are being pushed through the ground until we reach the receiving location. So the generic term there would be pipe jacking as opposed to conventional tunneling. So moving on to look at some types of excavation methods that may be going on at the front. As I mentioned earlier, you're seeing on the left-hand side of these photos a hand tunneling installation. So in this case, you see a fixed liner, and I'll elaborate a little bit more in a few slides on that, but you're seeing a type of liner there that's not moving. And we simply have workers at the front using pneumatic spades to dig at what you can see is a very stable face. And advance the tunnel in that way. They'll excavate far enough forward to be able to construct the next ring of liner, and the tunnel simply proceeds in that fashion. You will see in the case studies we present that the ground that we're working in for a few of these case studies is definitely amenable to this hand tunneling type of approach. Basically, if you have good stable ground without groundwater, then this can be a very good approach. The middle two photos are showing a couple different types of rotary TBMs or tunnel boring machines. So in this case, you're seeing mechanized equipment that has various types of cutting teeth that are rotating to dig at the ground at the face. And then that material is ingested into the machine. And as I said, usually in this case, brought typically with a short conveyor section to then put in a haul cart to be brought back to the launch location. And then finally on the right-hand side, you're seeing what would be termed a digger shield or an excavator shield. And the little yellow digger arm that you see projecting in the upper left portion of that shield is reaching out to dig at the ground. One item of note here is in that hand tunneling example, you don't see any real face support. That ground is completely supported under its own strength. And the first TBM does not have a lot of face support. But in the third photo from the left, you see that there's pie-shaped openings are the only place where ground can move into that particular type of TBM. And those pie-shaped wedges, the operator can actually change those so they become even smaller. So that type of shield can be used in ground that needs a little bit of support or the ability to control how much material can come in. So there is some face support available. And then similarly, in the excavator shield example, the three horizontal lines, I guess, that you see going across the face are louvers that can be rotated forward to be in a closed position or to block a portion of the face. And the operator can independently control those to close off a significant portion, not the entire face, but a significant portion, again, to provide stability. And then they can rotate just one of the louvers out of the way to dig in that particular area. So these shields have some ability to support certain types of ground that may not be fully stable. So moving on to the next slide, let's talk a little bit about the applications for this type of tunneling approach. Open face tunneling and pipe jacking methods are typically ideal for larger diameter installations in stable soils and rock. So by larger in this case, that can be a relative term. We mean about 48 inches in diameter or larger. The reason really for having that bottom end of what's practical is because we have people inside the tunnel. Because there's folks in there doing the hand tunneling or running the TBM or the other equipment. It's pretty difficult to work in a space smaller than about 48 inches. That's not to say there have not been projects in smaller tunnels. There have, but they're pretty rare and very challenging, I guess, to construct. You probably will not see TBMs smaller than 48 inches. Because the excavation face is completely open to the soil, or at least it's not sealed, it's not watertight, this type of method is going to be applicable typically in ground with either no groundwater or very limited amounts of groundwater inflow. That limited flow may be because you've got a groundwater table that's only a little bit above the invert of the tunnel, and so there's very little head pushing that water in, and so you have minor amounts of water coming through. Also, typically, if you were going to use this type of method below the groundwater table, you would want to be doing it in low permeability ground, so clays or silts, where even if you had some more head, even perhaps the groundwater head is at or just above the crown of the tunnel, the low permeability of the material means that very little water can actually come in at any particular time. It is possible to advance these tunnels in stable types of ground with some groundwater coming in, but it's a lot more common to use in dry conditions. And one of the significant advantages to using this type of methodology is if you find yourself in ground with rocks like cobbles or boulders, or even certain types of fill that may have chunks of fill debris in there, depending on exactly the type of shield you're using, you can often handle those types of rocks and get them inside the tunnel. If you are, encountering an occasional large boulder or large piece of fill debris, it may require extra special work by the contractor to break that obstruction or large rock into smaller pieces, perhaps to drill small holes and use very small explosives to split the rock, but it's often possible to get those things inside. As an item of note to maybe write down for future use, if you're doing a tunnel and you expect there to be large rocks or debris equal to about 40% or so of the diameter of the overall tunnel, it's pretty reasonable to expect that that can be handled using open face techniques. If they're bigger than that, it's not to say you can't get through them, but it's going to be more challenging. All right, on the next slide, we'll talk about limitations of this method. As I kind of touched on, the corollary of where this methodology is useful, where it can be difficult and you can run into issues, is there is very limited ability to control groundwater inflows. even those two shields I showed you with the pie-shaped openings that can be closed down, or the louvers, the sand shelves, they're sometimes called, those machines can't completely close off the face, and they're not watertight. So if you're in ground that's making a large amount of groundwater, whether it's just a permeable sand or gravel material with lots of groundwater head, you're not going to be able to stop that water flow through the tunnel. And the big issue that we worry about in that situation is, as that water is moving into the tunnel, it may drain to the shaft. Maybe you have pumps that can pump that water out. But the big risk is that as it's entering the tunnel, it's carrying soil particles with it. It's carrying sand particles, silt particles through the tunnel, depositing them, inside the tunnel or in the shaft. And what we're doing that whole time that the water is flowing is you're creating voids outside the tunnel. We're over excavating material. And that can lead to voiding in the ground, and then eventually, as the soil above moves down into that void space, settlement of overlying features. As I showed you, there's limited face stabilization depending on the specific type of shield that's used. There are ways that certain types of unstable faces can be supported, but as I just said, in unstable wet conditions, which might be termed fast raveling or flowing ground, we worry about over excavation. In loose sandy material, even if it's dry, sugar sand or beach sand kind of material, that type of sand may still be running through. Even with your sand shelves closed, there are gaps in those shelves. You may still be losing material into the tunnel in that type of ground. And then very soft clays and silts can squeeze into the tunnel. So anybody that's maybe familiar with young bay mud in the Bay Area or other types of very soft clays around the country, that can still be a problem in an open face tunneling situation. Just to throw some numbers at you, I talked about why you're pretty much going to see 48 inches as the bottom end of open face methods. We're showing you here a top end, but that's kind of an aberration, and it's specific to the fact that what we're presenting here today is trenchless methods. And trenchless methods, to most people, typically is referring to utility size tunnels. A lot of dry utilities like electrical, maybe oil and gas, water, sewer types of projects. So in that context, you're typically going to see these kinds of methods up to about 144 inches, but that's very approximate. And the same type of tunneling methodology is used in much bigger tunnels for transportation work, for really large water conveyance and storage type projects that go up well beyond 12 feet and into 20 feet and even larger. So that's not a fixed top end for this type of method. It's just that that's about the place where we kind of tend to stop talking about things as being utility tunneling or trenchless methods and maybe just refer to it as tunneling. Another number that again is very approximate. I don't want you to take this as a hard fact that we can't go more than 1,000 feet. But if we are pipe jacking in that scenario where we're pushing the entire tunnel liner forward, you will often see a practical limit of about 1,000 feet. Again, this is not a hard number. It's definitely possible to do longer than that. But a couple of reasons why you tend to see things truncate at about 1,000 feet is jacking force management. As we're pushing all that pipe through the ground, there's friction on the outside of the pipe that has to be managed. There are certainly ways that contractors can do that. And when we get into methods like microtunneling, that isn't within our scope today, but you may be familiar with the microtunneling method. Those tunnels are now routinely going 2,000 and even 3,000 feet in a single drive. But the lubrication that can be done with those tunnels is a little bit different and easier to do. Here, if we're trying to manage the injection of slippery lubricant materials outside of the jacking pipe to help it advance, with an open shield setting, the biggest issue is that lubricant can come around the front and start coming into our excavation, which just kind of makes a mess. So lubrication's a little trickier. And then the other reason that you sometimes see or often see tunnels truncate around 1,000 feet is that those haul carts that are being used to move material in and out of the tunnel are typically of a fixed size. So when you're advancing a tunnel and you're 300 or 400 feet in, it takes some amount of time to advance the tunnel forward and fill the haul cart. And then the haul cart drives back to the shaft, it's lifted out and emptied, and it comes back to the front. As the tunnel gets out longer and longer, it takes the same amount of time to fill the haul cart, but it's taking a longer and longer time to drive that haul cart back to the shaft and then back to the face again. And so there's this decreasing productivity that's occurring as the tunnel gets longer and longer. And somewhere around 1,000 feet, it often gets to the point where the productivity isn't great, and you might either see a contractor wanting to switch to a different method like microtunneling that doesn't have the haul cart issue, or just stopping the tunnel and having another shaft and then continuing if you need more trenchless length. So then lastly on this slide, the type of accuracy you would normally expect out of this kind of methodology is about plus or minus 2 to 3 inches in line or grade. Certainly in good ground conditions with a very careful contractor, you can do better than that. But generally speaking, you should expect about plus or minus 2 to 3 inches as the accuracy. All right, next. We'll just show you briefly some of the types of support that you might see depending on whether we're talking about conventional tunneling or pipe jacking. In conventional tunneling, in the size range that we're covering today, which is mostly about 84 inches and smaller, you most commonly see segmental steel tunnel liner plate. So that's the photo on the left is a liner plate tunnel, and then the middle photo is just a stack of those plates on the ground surface ready to be sent down and installed. And so you see that these are installed in rings, so every 16 to 24 inches usually is the width of these rings. A new one is erected, and they're put together in segmental panels. So depending on the diameter of your tunnel, it takes a different number of panels to complete a full ring. And as the tunnels advance, we just keep adding more rings to that system. Very common approach, especially in Texas, where 3 of the projects we'll talk about today were constructed. And then on the right, you see steel ribs with, in this case, wood lagging. So in this system, every several feet, every maybe 3 to 6 feet, a steel ring, essentially an I-beam or a W section that's been bent into a circular shape, is put up, and then in between each rib is lagging. And like I say, here you're seeing timber, wood lagging. You will sometimes see contractors using steel lagging, usually made of C-channel material. Or even in some rare cases, concrete lagging. Another type of conventional tunneling support you might see, but not very often in open face installations, is segmental concrete liners. So in those types of systems, these are precast liner segments that are made of concrete, reinforced concrete, but they're often gasketed in between the segments so that they can be used in tunnels where you do have groundwater or other types of unstable ground. They can completely seal the tunnel as they're installed. But as I say, usually they're fairly expensive to manufacture, and if you've got very stable or dry ground that favors the use of open face tunneling, it'd be pretty uncommon, not necessarily never used, but it's uncommon to see those used. You typically see that more with slurry shields and other types of closed face tunneling methods where you also need a watertight lining system. So then moving on to the pipe jacking types of installations and the liner that we use there, which typically instead of calling it a liner, we just refer to it as jacking pipe. The types of pipe that you'll see used on these larger diameter types of jacking projects, we see a lot of steel casing pipe. And so that's what you're seeing in the left and on the right. The left photo is a piece of, I believe that was 96-inch jacking pipe being installed on a project, and then some of that same pipe stockpiled at the site. In the middle photo, you see reinforced concrete pipe, in this case with a PVC liner for sanitary sewer flow. The PVC liner is there to try to protect the concrete from hydrogen sulfide gas. There's also fiberglass reinforced pipe, FRP. You may know it as Hobos, or there's also Thompson Pipe Group makes pipe. Those are 2 manufacturers in the US, and then there's some others around the world. And then there's also something called polymer concrete pipe, which is pretty rare in the US. It's a pipe material that uses polyester resin to bind aggregate. It's kind of like RCP, reinforced concrete pipe, except with a polyester resin instead of cement, though that material is typically only manufactured these days that I'm aware of in Germany, and it's a little difficult to get. Okay, one last slide I think we have before we move on to our case studies. And that's just a couple of thoughts about when would we choose one of these methods over the other? When would you consider one method versus the other on a project? So the conventional tunneling method is typically favorable in stable ground because it makes it easier to excavate enough ground to put up the next ring of support. It can, again, in these smaller types of installations that we're talking about in the 48 to say 84-inch range, result in smaller shaft requirements because there aren't hydraulic jacks and some of the other equipment necessary in the shaft to be able to push 20-foot or sometimes even longer sticks of jacking pipe. The shafts can often be smaller in those settings. Again, in much larger tunnels, where you're still using open face methods, you may actually need a much larger shaft because the tunneling can get a lot more complicated. But in utility sized tunnels, the shafts are often a little bit smaller. It can be flexible in mixed conditions, meaning if you've got a little bit of a mixed face or some changing ground conditions, there's times where the conventional tunneling approach can be a little bit more flexible to handle that ground if it's stable. If we're trying to tunnel in more unstable ground conditions, that may require a tail shield. That is a part of the shield at the back that will support the ground so that after the shield is pushed forward off of the previous ring of lining, there's now space that's protected from the ground to build the new ring before the shield is pushed forward again and that new ring is exposed to that ground to keep everything safe, especially the workers, and keep the tunnel supported. Because putting up these rings of lining is often a little bit more complicated and time consuming than just dropping in a new piece of jacking pipe, you often see a little bit slower production rate out of conventional tunneling. Pipe jacking can be more effective sometimes in less stable ground because the operator can be advancing the casing pipe at the same time that the tunnel is being excavated. So every inch of tunneling advance rate, the casing can be pushed immediately to support the ground in that type of situation. We do, however, have to manage jacking forces, as I talked about, in terms of using lubrication to keep the jacking forces moving. And typically, as a corollary to what I just explained for conventional tunneling, you'll often see at least a little bit higher daily production rate simply because it's faster to install the liner, if you will, because all we do is drop a piece of jacking pipe into the shaft, connect it, which can take a little while if we're welding, and then go back to tunneling. So those are just some thoughts to put in everybody's mind, some considerations for the types of tunneling that we're now going to talk to you about. And with that, I'm going to hand it to Nathan, and he's going to go over the first case study.
Thank you, Matt. What a great introduction to our topic for today. So, hello, my name is Nathan, and I'm located in the San Antonio office. Today, we're going to provide you some tunneling insight on the W9 sewer project for San Antonio Water System. For reference, this project is located on the west side of San Antonio and was identified by SAWS to meet future flows due to growth in this particular sewer basin. Next slide, please. This project is a 48-inch diameter sewer interceptor that's approximately 24,000 feet in length, with over 10,000 feet of that being tunneled. The alignment follows Leon Creek through the San Antonio Park's network of trails and is contained to the 100-year floodplain. The tunneling segments were selected to minimize impacts to not only Costa Park trails, but also maintain tree canopy and cross deep sections. The yellow lines displayed on your screen onto the left indicate these locations and currently the project is on schedule with construction to be completed in August of 2026. Next slide. Since this is a sewer project, we're limited to where this can be constructed, and that's mainly due to the location of the existing sewer main and how the overall system is interconnected. Keeping the new main near the existing one was key, and because of it, several challenges were presented to the design team, and of these challenges that included construction occurring in a 100-year floodplain, even though it's a dry creek bed, navigating city parks and a trail system while maintaining public access. You can see photos of the pretty trails and the tree canopy that we're trying to preserve while minimizing environmental disturbances. Difficult access due to heavy vegetation, narrow corridors, and the fact that we're down low into a creek area. And then due to topography challenges, deep sewer segments that are greater than 30 feet and that are through hard rock. And so these areas, tunneling was selected to mitigate those challenges. Next slide. So due to these challenges that this project presented, locations that were tunneled were selected, and obviously to keep the park trails operational, that was critical with our partners that we're working with. Reducing impacts to the heavy vegetated area. Here in Texas, when the sun's out, it's very hot, so keeping tree canopy was definitely a priority with the Parks Department, and keeping that natural look, feel that we'd be traveling across. And obviously crossing some deep segments based on topography that, because pipe is gravity flowed, being sewer, we have to maintain that through the whole alignment. So picking alignments to keep that progress was key, and tunneling would help us, and it would minimize some of the deeper cuts excavators would be required. To provide the contractor flexibility in this tunneling method, the team agreed in writing specifications to allow the contractor to have a range of diameters between 72 inch and 84 inches. This gives the contractor the flexibility to use existing equipment they may have had readily available from another job site, or if they're hand mining and they want to have additional room to work, obviously comfortability, it gives them a range that they can work within. Obviously, unit prices would be reflected based on this range, and the contractor, whichever they selected within that diameter, would be held to that unit price. There would be no negotiations or changes in value. So you have a range, you select tighter or larger, more material, less material. Ultimately, if you build it within this diameter, everybody will be happy. And so then due to the soil conditions, the design team also allowed the contractor to select their preferred open tunneling method, whether that be rotary TBM, road header, or hand mining. Again, giving the contractor flexibility based on the equipment they had available, with this having 10,000 feet of tunnels and having a relatively large range and size, wanted to make sure we had a good list of contractors that could be available to be a part of this project, and not limited based on the equipment, and to give that the flexibility. Ultimately, as Matt had noted, this project was selected and the contractor utilized hand mining. You've got a photo of the operations that occurred recently. Since the carrier pipe is going to be a 48-inch FRP, a specified casing can either be steel ribs or lagging, or steel liner plate. And the particular contractor elected to go with steel liner plate. It's something that they're very comfortable with, and as they hand mine and a stable rock, they're able to progress, add their plates, and keep moving forward. This gave the contractor lots of flexibility. It opened the opportunity for more contractors to bid on the project, ultimately providing cost savings to our clients. And to date, 95% of all the tunnels have been constructed. So the next part of the phase is threading with the carrier pipe and wrapping up the tunneling portion. Next slide. So as you can see at the bottom of the page, where the project connects to the existing sewer, this was a particular challenge that the design team faced, and it was ultimately with the alignment. So as you note that this is going to be following a curved creek bend, and if we stayed straight and true with the original alignment, we would be very shallow, and ultimately erosion of the creek would remove material that would be above, and then obviously daylighting the casing, which is what we would not want to have. So looking at this challenge, the design team, along with our partners with saws and pipe manufacturers, we reviewed what kind of radius could be achieved and could it be tunneled. So through all of our coordinations with Matt and his team, with saws and their staff, pipe manufacturers, it was ultimately agreed that an 800-foot radius could be achieved by utilizing 10-foot sticks of 48-inch FRP pipe, and that would be allowable based on deflections at each joint coupling. The contractor provided a detailed submittal on how they would achieve this specific challenge for the project. It was reviewed by multiple parties, and they also noted that they would survey every 50 feet and confirm that both radius and pipe grade would be followed. To date, the tunnel has been completed, and they were within all of our specifications. So it was a great success, especially to see curved to gravity sewer in a challenging location. And I'm glad that that all was successful, and it was going to be a great contribution to the SAWS system. So now I'm going to pass it over to Matt to talk about some additional insight regarding the tunneling methods considered for this project.
Yeah, thanks, Nathan. Yeah, just a couple of quick notes on options that we allowed or how we came to allow things in the specifications. What you're seeing here is just one of the particular sheets from the GBR on a couple of consecutive tunnel reaches for this project. The GBR included these profiles that showed the different ground units that were present. And what you're seeing in the brown, yellow, orange colors on the left-hand side is this gradation of clay soils at the top transitioning to something in between very hard soil and very weak rock, something known as intermediate geomaterial, IGM. And then finally transitioning in the brown layer to marl stone, which is, again, kind of a very soft clayey stone, but a rock material. And then on the right in the blue, in this particular area, you see a transition into, it's more clay soil. So these aren't dramatic differences in material, but there was quite a significant change in the plasticity when you got into those blue soils on the right-hand side. It went from being a low plasticity, drier clay material into something that's a lot stickier. Then you also see there's a blue line that is down below, well below the invert on the left-hand side of the page, but then comes up and is above the crown on the right-hand side, and that was the groundwater elevation that was indicated in the borings. And the far right side here is crossing a creek. So that context, you know, came into play when we were considering whether we wanted to just specify that only hand tunneling should be used, or whether TBMs or other types of mechanical machines were allowed. There also was an issue with karst on this project. The north end of the alignment, there are a couple of karst features, which, if you're not familiar, these are solution cavities that can form in primarily limestone rock, where some of the minerals have been washed out over time, and you essentially have voids or caves. They can vary in size from just a couple of fistfuls to, in some cases, many feet in size. And there were a couple that were known and mapped near the alignment on the north end of the job. We never encountered any in the geotechnical investigation, so it's difficult to know for sure if there would be karst in any of the tunnels, but there was certainly a risk of it. So for some of those reasons, there were segments of the job where we limited the use of rotary TBMs. We were nervous about the idea of having rotary TBM in the ground if it encounters especially a large karst. The shield might start to fall into such a thing and become wedged in place. And so hand tunneling offers a much greater flexibility to handle those types of changing conditions or potentials for karst. The highly plastic clays, sometimes in a TBM, really plastic clays might get sort of clogged in the openings. If it's very sticky, it starts to stick all over the tooling. And so that, combined also with the fact that in this part of Central Texas, hand tunneling is very common and the contractors are quite comfortable with it, we did limit the use of TBMs on a few of the crossings where we thought karst was more likely, or we knew that there were these highly plastic clays. We preferred the flexibility. And then one other note on the next slide, just the issue of going with fixed lining versus pipe jacking for these crossings. For primarily the same set of concerns about the highly plastic clays, karst, and some notes about lubrication that I touched on earlier, we discussed whether we would stick with just fixed lining of liner plate and ribbon lagging, or whether we would specifically allow, I guess, pipe jacking. And again, because the highly plastic clays are a little bit more challenging in terms of jacking forces and the need to lubricate, and then again, also the issues with potential for karst, and then finally, again, the fact that in this part of Texas, it's far more common for most, not all, but most of the contractors to prefer doing hand tunneling with liner plate. We did limit the design to just allowing fixed linings with hand tunneling, and as I said, with certain types of mechanized tunneling at the face. So I think that wraps up our discussion for this project, and Shelby is going to speak about a project in Dallas, or Fort Worth, sorry.
Thank you, Matt. So like Matt mentioned, my name is Shelby Warchesick. I work in Kimley-Horn's Fort Worth office. Today I'm going to talk about our Westside 3 42-inch water transmission main project. The project is currently in undeveloped pasture land, but really the overall purpose of this project, along with many other projects in this area, is to provide water to the west and southwest parts of Fort Worth that are rapidly developing. Next slide, please. So the image on the left of the screen is our overall project map. This project was split into 2 separate phases. The main purpose for the phasing split was due to some challenges with easement acquisition on phase 2. Overall, phase 1 consisted of a little over 20,000 linear feet of 42-inch pipe, with 700 linear feet of that being tunneled construction, as well as a 1,200 linear foot section of 36-inch pipe with 560 linear feet being tunneled. The second phase had 5,200 linear feet of 42-inch with 880 linear feet of tunneled construction. I highlighted on the map the areas in red where we had tunneled crossings, and these were mainly the crossings of gas lines, major highways, or major creek crossings. For the purpose of this presentation, I'm mainly going to be talking about the tunnels for the 2 highway crossings on this project. Next slide. For phase 1, this is where we cross IH-20. On here we have our parallel 54-inch and 66-inch tunnels. Our initial consideration during design was putting these within a singular tunnel. However, when we started to look at the overall volume required to do this, it was significantly higher, and so it just made more sense to make these 2 separate parallel tunnels. With the parallel tunnels, we did want to keep a minimum of 2 to 2.5 times the largest tunnel diameter between the 2 tunnels to ensure there wasn't any issues during construction between the 2. We also wanted to consider the depth under the highway. There were some proposed TxDOT improvements planned for this area, and so we wanted to ensure there wouldn't be any conflicts or future settlement in the area. For the overall project, we did allow for either steel casing or tunnel liner plate, and we didn't put any real limitations for how the tunnels were to be completed. Overall, like Matt mentioned, hand tunneling is very common here in North Texas, so that is what we anticipated for construction. Next slide. Once the project was awarded to the contractor did elect to use a tunnel boring machine with 4-flange tunnel liner plate. From our geotech report during the design phase, we did anticipate very hard rock in the area, so we didn't anticipate this being an issue. However, once they made it about 1/3 of the way through the tunnel, they did encounter some soft soils. We were concerned that the tunnel wouldn't be able to continue progressing, and we started thinking of how are we going to retrieve the TBM if this were the case. Fortunately enough, the contractor was able to progress forward. It was at a much slower rate, but they got through the softer soils and finished the tunnel successfully. So our next phase of the project is phase 2. Here's where we cross I-30. What's shown on the image on the screen in the shaded gray are proposed highway improvements in this area. The highway improvements in this area were much more extensive than what we had on I-20, and the design wasn't very far along, and so we did have to make some assumptions on what the final improvements would be for the highway improvements. Overall, we did know that they were planning for an overpass here, and so we did have to take into consideration where the drilled shafts would be located, how deep those would go, to make sure we didn't have any conflicts with our proposed water line. Also, on the south side of I-30 is the area that we did have issues with easement acquisition, and so both for this highway crossing and the other tunnels on this phase, we did have some very constrained work areas that the contractor had to work around. Next slide. Also during design, we had to take some special considerations in for the profile of our water line. And so on the profile shown on the screen, we've included some snips of our geotech report, and the areas highlighted in red, those are the areas we anticipated the softer soils. And then the brick hatching, that was the harder limestone that we had experienced on a lot of this project. And so on the south side, which is the left side of the profile, we wanted to ensure that we were deep enough to be fully within rock and not experience any mixed face conditions there. And then on the north side, we could have shallowed this side up some and still be fully within rock. However, then we wanted to take into consideration, if we did shallow it, our slope would be quite steep and could limit some tunneling methodologies such as hand tunneling. Overall, in this phase, the contractor elected to use hand tunneling and with 4-flange tunnel liner plate. And so they're about halfway through this tunnel currently, and looking forward to a successful completion. So with that, I'll transition it over to Eric.
Yeah, good afternoon, everybody. I'm pleased to be able to tell you about a project our team has been working on in Laughlin, Nevada, which is just southeast of Las Vegas, which is the Kimley-Horn office where I sit. The project is all-encompassing, I should say. It's includes some lift station improvements, some wastewater treatment plant improvements, some gravity sewer CIPP rehab, as well as replacement of an existing ACP and DIP force main. So it's 2 miles of existing 16-inch force main out there crossing the desert, and the project will replace that single force main with 2 dual side-by-side 16-inch HDPE force mains, and then that's followed by 1 mile of 21-inch CIPP to take us all the way the rest of the way to the treatment plant. So along the project's alignment, there's a couple of spots where our team began to consider use of trenchless methods. And ultimately, as you'll see here in the discussion, we ended up using open shield pipe jacking for our trenchless engineering proposal on the project for up to 500 feet or so. At the existing lift station, there were some improvements that included adding a surge tank, a bifurcation to split the single discharge main or discharge train at the lift station into 2 so that we can have those 2 force mains. Additional valve ball, additional flow metering, and then once we get to the wastewater plant, there was a concern about the configuration that caused some ragging in the EQ tanks, and so our improvements included a screening structure and diversion structure to help coordinate some of those some of those operations. If you would, next slide. So as I mentioned, the project, we started to consider trenchless methods for a couple of different spots along the alignment. In the photo on the left side, you can kind of see those three areas highlighted: drive 1, drive 2A, and drive 2B. As you can see in the rough profile view on the bottom right, the purpose of drive number 1 was to cross underneath a relatively large earthen mound. I wouldn't call it a mountain since I live in the Southwest United States. Mountains are a lot bigger than that here, but it's substantially tall, and there wasn't an opportunity for us to go out and around it because of existing property boundaries and easement restrictions, things like that. And so we were obligated to either have a trench that would be something like 60 feet deep, or to use trenchless methods to go underneath it. So we began to consider a number of different evaluation criteria, which are listed there in the bullets. But the second two spots, drive 2A and 2B, the goal here was that the client for our project was eager to maintain their standard of having a continuously uphill grade on force mains, so as to alleviate some air pocket type concern for air releases and just continuity there. So in order to maintain a continuously uphill grade, it was either, again, facing a significantly deep trench, or which would be installed through open cutting, or use trenchless methods. Now, we ultimately disqualified drive 2A and 2B from the project in terms of trenchless methods. We did end up, proposing a open cut installation there that I think achieves around 30 feet in depth for its total trench depth. Not the worst, but still not our favorite. But yeah, so our focus for trenchless engineering on this project remained isolated to just drive number 1, and so we began to evaluate it using those criteria of, like, well, what kind of soils are we facing? What steerability will we have? What kind of impact will it have in terms of settlement to other existing utilities and structures nearby? Is the diameter suited for whatever method we end up using? And then, what are the geotechnical conditions? And I'll mention here, just I saw in the questions there was a question about what the delivery method was for each of the projects we're presenting on. So this one is a design, bid, build project, conventional methods. So I think that might cover it for me. So I want to bring Matt back in to help us present on some of those considerations. Oh, not quite yet. So one more, I guess, and then Matt can join us. It's this is a profile view showing the area of trenchless methods, or the area of trenchless engineering. It's, again, 500 feet long or so. And I mentioned diameter as one of those criteria a moment ago. We ended up proposing a 60-inch diameter steel casing with a spacer in there that can carry both of the 16-inch force mains inside it. If we had used isolated casings or individual casings for each of the force mains, then the casing would have been too small to use some of these methods that Matt has described for where a manned entry takes place. A person is inside the casing. So by using this larger diameter and sharing the space inside for both force mains, we're able to open up the opportunity for other methods that would enable open face person inside the trench. All right, sorry to jump the gun there, Matt. Let's have you join in and take us to the finish line on this. Thank you.
Sure, of course. Yeah, so just some quick notes again on how we came to the specifications and what methodology was ultimately put out for this project. The ground here was dry ground with quite a bit of gravel and cobbles as well. We also had a fairly short tunnel length, for the single crossing that was being designed here. And so this favored the use of open face methods. By having an open face tunneling approach, those cobbles could be far more easily ingested than if we were using some type of closed face method like microtunneling. But then the sort of less stable nature of this material, and what I mean by that is, in this case, we had a sandy, gravelly material with cobbles. It doesn't have the cohesion that the clay materials that we've talked about on the last 2 case studies had. There's a potential for raveling of that material into the face, and it's unlikely that it would stay stable, over a 2-foot free span of excavation to put up a liner plate ring or something like that. So in that less stable ground, it favored the use of pipe jacking over tunneling. So as I mentioned before, that allows the casing to be pushed forward continuously at the same rate as the excavation, keeping everything fully supported as you move along. Using conventional tunneling methods in this type of tunnel would require that you have a shield with a tail skin on it so that you could put up the rings of support behind you. And it's not that that couldn't be used in this situation, but at 60 inches, it's kind of small for the types of shields that are built to do that kind of work. And then really at the, only a few hundred feet of length that we had here, that equipment's pretty complex to mobilize and get set up for a single crossing that's that short. And simply jacking steel casing is a lot more straightforward approach. So ultimately, that's what the specifications allowed here was open face pipe jacking with steel casing. So I think that takes care of this case study, and Stephen Kelly is going to present the last of our 4.
Yeah, that's right. Thanks, Matt. So just to quickly introduce myself. So my name is Stephen Kelly with Kimley-Horn. I sit here in our Houston office, and today I'm going to talk about our West Harris County Regional Water Authority contract 65 60-inch water line. So our project is, so on the map you see kind of the greater Houston area. Our project is on the west side of town, kind of nestled between the 290 and the I-10 corridors. So a little bit more about our project description. It is approximately 3,000 feet of 60-inch steel water line. So we had 4 tunnel segments on this project in total of varying lengths, anywhere between 20 feet to 300 feet. All of it was 84-inch. They were 84-inch tunnels, open face with smooth tunnel liner plate, and we'll circle back to that here in a minute. But overall, the ground conditions in the Houston area can generally be categorized by a mix of hard, stiff clays, also soft clays, with pockets of sand seams, and generally high groundwater, but that can vary anywhere between a couple feet below the surface to quite deep. So we never know what we'll see, and things just seem to be consistently inconsistent. And so we affectionately like to call our soils around here gumbo clay. So the segments that we're going to specifically focus on for now are highlighted in solid yellow. So the other 2 tunnel segments that I mentioned, those are in the dotted lines, but those are our Barker Village Lane crossings and our West Little York Road crossing. So both of them, the common thread between them is just proximity to other things, with Barker Village being close to other existing utilities, and then West Little York being close to some other structures, and then we'll talk about some of the design considerations of each. But before we jump into that, I'll pass it back to Matt. He's going to talk through some of the trenchless considerations we had on this project as they apply to kind of both of these focus areas before I come back and share a little bit more of the details. So I'll welcome back Matt here.
All right, thanks, Stephen. Yeah. One more brief note before, Stephen will tell you some specifics about those particular crossings. But just to set the stage again for these 2 crossings, this was dry, stiff to hard clay conditions in all of the borings for the crossings here. So it was pretty straightforward, very stable ground, quite short tunnel lengths. We'll talk about 2 of the longer ones, but they're only a couple hundred feet. The specifications in this case, we did what we would prefer to do in most cases, which is allow as many methods as are technically feasible. And we felt that both open face pipe jacking and open face tunneling methods were practical for use here, and so they were both allowed in the specs. And ultimately, the contractor proposed to use a rotary TBM advancing off of smooth tunnel liner plate. So you're seeing the photos on the right-hand side are from their submittal, from their shop drawings that they sent in as the machine that they were going to use. And the smooth tunnel liner plate's interesting. You may have noticed in the photos I showed earlier that typically tunnel liner plate is corrugated. There are corrugations in each plate that make it a little bit stronger for the same thickness of steel that you would otherwise have. So for smooth tunnel liner plate, the disadvantage being it typically has to be a little bit thicker for the same type of ground loading. But from the contractor's perspective, they didn't explain to us exactly why they did this, but I suspect that it was because the smooth plate without the corrugations lets them keep a tighter tolerance, a closer tolerance between the inside diameter of the shield and the outside diameter of that liner plate. So the annular space that gets created between the maximum excavation of the tunnel and the OD of the liner plate is smaller. It gets kept a little bit tighter because you don't have those corrugations to accommodate. And so I believe that that's their reasoning. So anyway, those quick notes on sort of what the tunnel approach was, and I'll hand it right back to Stephen to share some specifics.
Yeah, thanks, Matt. So talking first about Barker Village Lane, what we were dealing with here is just proximity to existing utilities, and so there were three that we were relatively close to. It was a 6-inch force main, a 12-inch water line, and then an 8-inch wastewater line. So we essentially had kind of two options in this area for how to develop our profile and design our tunnel. So we could either kind of thread the needle between these between these three utilities, or we could drop our tunnel underneath the wastewater line. So ultimately determined that the risk for threading the needle was pretty low. We could utilize some practices that help minimize risk that I'll get into in just a second. And we had some good record information for these utilities. They're not that old. They were relatively new. We had complete record drawings and generally had a good idea of where they were. So one of the first things that we could do for this crossing was just require critical locates for each of these utilities. And so that's kind of what you see in that left graphic is the plan view of our plan sheets and how we specifically called that out. So it refers to a specification, and this is typically it's just achieved by excavation or level A SUE. It's performed by the contractor in advance of the tunnel or the water line installation, just to verify that the clearances are we have sufficient clearance and the conflicts are cleared. And if there's any things that we need to address or address between the installation and when they're actually out there mobilized and doing stuff, we have some time to do so. So we wanted to make sure that we called out things like that. And then the other thing that we wanted to include in our design is just making sure that we had what I'll call utility excavation relief pits, which is essentially just removing the soil on top of the utility, exposing it, daylighting it, and then excavating down around it a little bit, just so that you are minimizing any disturbances created as the tunnel machine passed. And as the tunnel is completed, then you backfill that, and you can backfill it with different things, but it's easier to use like a CLSM or self-compressing material, cement stabilized sand, controlled load strength, something like that, just so you don't have to worry about any compaction requirements as you're backfilling that. So this tunnel section isn't complete yet. It's almost getting ready to be started soon. So hopefully there'll be an update to share in the next few weeks, next couple months. So moving on. Okay, and then the next segment I'm going to talk about is our West Little York Road crossing. So just to kind of orient ourselves, the tunnel basically went south to north. Our launch shaft was in that concrete paved area, and then approximately 300 feet away was our receiving shaft. this was 84-inch tunnel. And then you can see just from the graphic of how close we were to an existing business. And so this was about 14 feet away, basically from the edge of their slab to the center of our water line. And so we were 60-inch water line with 84-inch tunnel, so it was close. So a couple of the design considerations that we had to work through were just the general ground conditions from our geotech. So I saw a question earlier in the chat, so I'll try to answer this for my project. But for geotech, we got a bore at the launch and the receiving shaft, or just north of the receiving shaft, and then we got one specifically on this property, kind of in their front yard area, almost right where it says the S for settlement monitoring. And what we discovered was that the soils in this area were generally pretty stiff clays, which is good, except there was a sand seam and a sand pocket that was about 23 feet deep. So that kind of limited us in terms of how deep that we could go, and we wanted to stay out of that, which kept us a little shallower. And so in order to kind of mitigate some of that risk as the machine is passing by this area, we had to instill some settlement monitoring measures. So, and that's what you see in the red circles. So we had 4 specific locations, basically 2 over the center of our tunnel, and then 2 right on the corner, the 2 nearest corners of that building. And it was what we did is we had a detail in the plans, and we had some specification language. Basically, it was settlement monitoring from the ground. So it was essentially just an iron pin stuck in the ground that was surveyed multiple times before the tunnel passed, before the machine passed through, during tunneling specifically, and then afterwards as well. So we received just reports submitted by the contractor every couple of days that showed the progress of what they were doing, and showed the settlement monitoring just kind of graphed over time. And what we discovered was that the settlement monitoring was really helpful, and then the settlement itself was essentially negligible to plus or minus a few hundredths of an inch. So it wasn't a major concern for us as all. And then this tunnel is complete, and this the contractors continued work kind of up through the north side of the alignment. So that's what I have to share. I will pass it back to Marty for a quick summary, and then to close us out and get us into Q&A. So thank you.
All right, thanks, Stephen. So as a quick summary of what we talked about today, we've kind of done an overview of some of the open face trenchless technologies and their applications, and then we presented 4 case studies. The first one was the gravity sewer that was done by hand tunneling, and also included that curved section that you remember Nathan talking about. Then we also talked about the 42-inch water transmission main and the tunnels across the highway, parallel tunnels that Shelby talked about. And then Eric also talked about the dual force mains that were tunneled in a single 60-inch casing in Las Vegas, and some of the differing ground conditions in that area. And then Stephen just talked about the 60-inch water line and some of the challenges related to the close proximity of existing utilities and the existing structure. And so with that, we're going to go ahead and start looking at some of the questions. I see that there are several questions that have been placed into the chat. And so some of our speakers have gotten in there and started answering some of those questions, but I'm not sure that everyone is able to see all those. So we'll kind of go through and see how many of these we can answer in our remaining time, which we have about 20 minutes. So we should be able to answer quite a few. Why don't we start with one of the ones that has been flagged here. Matt, you want to elaborate on what Stephen just talked about as far as how do we monitor ground movements during the tunneling process?
Sure. Yeah, you know, Stephen covered one of these 4 projects where settlement was of particular concern and kind of described the simple way in which settlement is typically monitored, which is points constructed at the surface that may be, Stephen, you know, said in this case there were steel pins. You might also see wood stakes driven in the ground, and then usually with like a PK nail, a surveyor's nail, placed in that wood. In asphalt, you can also just hammer PK nails into the ground. In concrete, you might see the contractor take a chisel and just make an X inscribed in the concrete, so there's a specific point that they can survey each time. And then however those points are established, they are simply surveyed at least every day. In some cases, if you have critical things you need to monitor, none of these projects happen to involve railroads, for example, but in rail crossings, it's becoming more common now for the railroad companies to want really frequent monitoring, like multiple times per day at least. And one of the systems that's been a lot more common recently is robotic theodolites, I guess, or remote controlled theodolite systems that can be set up on site, and there are reflective targets placed on whatever features of interest, which again, in this particular example, it would be the rails of the railroad tracks, usually placed on the side of the rail. And then that system, every hour perhaps, could be slightly more or less often, will turn on and will look around and locate each individual point and take a measurement of each of those points, and then that's recorded to a system. And then of course these days it's likely wirelessly sent to some kind of a database where all those points can be monitored in real time. So those types of systems are becoming common if you have really critical things that you're crossing with sophisticated monitoring requirements. One other item that's probably worth noting is we have used what we call utility monitoring points. I don't mean to suggest that that's anything that Bennett Trenchless invented, but for if you're crossing a particular utility, there have been some questions that you may have seen us answer in the chat about what kind of clearance is needed for crossing existing utilities. If you're crossing one and whether the amount of clearance you can create is limited or you're just otherwise very concerned about that utility moving, you can excavate down to the crown of that particular utility, often with soft dig techniques like with vacuum excavating, because we don't want to damage the utility, of course. Place a casing, you know, a PVC casing pipe, and then some type of rod. It might be steel if that's compatible with the utility that you're placing it on top of, or it might be like fiberglass or something if corrosion is of a particular interest. And that rod basically is now touching the top of the utility and it comes up to the surface. And it now gives you a way to monitor any movement of that utility immediately while you tunnel underneath. So those are some of the common ways that ground movements and settlement are monitored on projects.
Great. Another question that may be of interest to several people is, what spacing between boreholes did you specify during your investigations? And so I think, Shelby, you put an answer in there for your Fort Worth project. You want to elaborate on that a little bit?
Sure. For our project, we got boreholes on either side of the tunnel, as well as about every 1,000 to 1,500 feet along the rest of the alignment.
Mm-hmm. And Matt, you know, in general, when you've got a short tunnel or a long tunnel, do you have some guidelines for geotechnical investigation? Yeah.
The general rule of thumb used in the trenchless industry is that we'd like to have borings at each shaft location, or if, you know, to be a little bit more broad than just the tunneling methods we're talking about today, if you were using, say, horizontal directional drilling at each end of the bore. And then every 500 feet in between, we'd like to have a spacing that doesn't exceed 500 feet. That's the standard guidance that you're going to see. That can be adjusted depending on what you may know about the overall setting that you're in. So if you happen to be working in a part of the country where the ground units are particularly consistent, and you have past experience that tells you that, hey, you know, we're very likely to see the same type of soil profile or ground profile along this entire alignment, because certain parts of the country are that consistent, that could be a reasonable justification for having a greater boring spacing and not necessarily having borings every 500 feet. And then of course, conversely, if you're in a part of the country where there's highly variable ground conditions, or just in a setting like, say, a river crossing, where the river has likely changed what the nature of the geologic profile looks like right at your crossing, that is going to warrant even closer spaced borings, because there's a good chance that there's a lot of variability in what the ground looks like over a short period of time. So there's certainly some judgment and experience to planning the geotechnical investigation and how close the boring should be.
Great. I'll pick another question out of here. There's a question about what is done between the tunnel liner and the carrier pipe, or the conveyance pipe. Somebody want to answer that one? How about Eric? You want to jump in there, or Nathan?
Go ahead, Nathan.
Yeah, so on the W9 job, the FRP pipe was threaded through the liner plate, and then bulkheads would be built on either side. They had a 1.5-inch PVC pipe that would full length of the tunnel, and they would start filling in annular space. Obviously, the annular space outside the tunnel liner plate as well to fill any voids that might have been overcutting with hand mining, but obviously the inside pipe would have rings with, sometimes it's all threads, probably large gauge, to hold the pipe centered so it wouldn't move, and then sometimes they also fill the pipe with water to reduce buoyancy, but ultimately a non-shrink, and they would pressure grounded to make sure that they would fill any kind of voids, and then that pipe essentially would be encased with that. I think we had specified about 50 psi at full breakage, so it's not rock hard, but it keeps nothing from moving within that period, and it fills up the voids. There'd be no water that would infiltrate later on.
Eric, when you had the special casing spacer to carry the two pipes in your larger casing, did y'all do anything in that void space between those?
So to fill the annular spacing inside the casing, yeah, typically our approach out here in the Southwest is to fill the annular space with grout or with cement slurry.
Yeah.
Certainly something to consider is the heat of hydration can have an effect on the carrier pipe of the utility as well. So something to consider when there's so much cement going into a casing like that.
Yeah, for sure. Okay, there's a question, I think it relates to Shelby's project. It says, in the case where there were parallel tunnels, how was the minimum separation distance between them determined? And did they end up in common sending and receiving shafts? Shelby, want to jump in there? Yeah.
Yes. So for the parallel tunnels, we took a similar approach as if it were a vertical crossing. So I think Matt answered in one of the other questions, depending on what the crossing is, we're about 2 to 2.5 feet apart from one another in a vertical crossing. And so we did a similar approach with the horizontal separation, where we took 2 to 2.5 feet separation between the two. And the main consideration was whenever they went to do the 66-inch tunnel, we didn't want it to have any disturbance on the 54-inch tunnel that was already completed. And as far as the receiving shaft question, they had separate shafts between the two tunnels.
Mm-hmm. Great. Matt, there's a question here asking about the cutter heads, if they're custom made for specific types of rock. You want to talk about that a little bit?
Yeah. like almost any question you ask a geotechnical engineer, you're gonna first hear it depends. I think that when you're in softer types of material, especially sedimentary rocks, a lot of these projects in Central Texas, when we're in rock, it's marlstone and sometimes limestone material that's usually only getting up to about 5,000 PSI and often is in the hundreds of PSI. Those softer rocks, I think you might get a rock head, a contractor might have a sort of rock head that they bought from Ackerman or whatever manufacturer of equipment you might get. That's not really custom designed. It is specifically designed for use in rock as opposed to being used in soil. That is definitely going to be true, but it's not necessarily custom made for that project. If, however, you are working on maybe a more complex type of rock style, like a conglomerate or a breccia, something where you have a matrix of rock material that's of a certain strength, but it has chunks of cobble or harder material that's in the matrix of the rock, or if you just have hard rock in general. And I guess what I mean when I say hard rock is, you know, beyond 5,000 PSI, 10,000, 15,000, 20,000 PSI rock. When you start getting up to those kinds of materials, it's more likely that you will have the contractor ordering a specific rock head for that project, that where hopefully information that's been gathered during the design and shared with the contractor about rock strength, about rock abrasivity, the mineralogy of the rock is being shared with the contractor specifically so that they can order a specialized head that will hopefully have the most penetration rate and the greatest longevity in those conditions that you're tunneling in. So I would say it depends on how hard and how complex the rock is, whether or not it's actually custom designed. But in any case, if you're in rock, it is definitely going to be a specialty head for that work.
Right. Matt, there's another question related to contractor pricing overall, compared between last year and this year on similar work. Are you seeing any volatility or you know, stabilization of pricing similar?
I will caveat it by saying that while we only do trenchless work, we're also not, we're kind of small, as I introduced at the beginning. So our slice of the pie isn't huge. I may pass it back to you guys to ask what you're seeing maybe more broadly. But what I will say is that, yes, there's definitely volatility in the market right now. And in general, costs are going up. For sure. You know, there's pressures, of course, that are being put on all kinds of different materials in the industry. And there's also just a lot of work going on. And so some contractors, I mean, again, this always varies, but there are contractors who don't have a lot of pressure on them at the moment to offer the best pricing that they can. So in general, I would say that tunneling costs continue to increase, and they have been doing so for, you know, the last 10 years probably. And there's definitely volatility at the moment in a lot of materials.
Right. Stephen, there was a question about the TBM used on the Houston project. It looks like you put an answer in the chat, but maybe not everyone got the chance to hear that. You want to talk a little bit about the TBM on the Houston project?
Yeah, sure, I can. So it was an open face tunnel boring machine. It was an 88-inch machine that was pushing an 84-inch liner, or not pushing an 84-inch liner, but with an 84-inch liner, and then had jacking rails to advance it.
Great. There's a question, Matt, when you were talking about different challenges with open face tunneling, you talked about different soil materials. You mentioned squeezing clays. There's a question about squeezing rock. Is that something that we've got experience with, or you've seen that before?
Not a lot, I would say. Squeezing rock is a pretty rare, at least maybe that's just unique to our experience, but it's not a particularly common condition to encounter. Now, maybe trying to be open to whether they literally mean squeezing rock or also swelling rock, which is a subtle difference that maybe only geotech nerds care about. But presuming, let's say we're talking about either, you know, there are certainly shales and other types of clay-based rocks that will swell when you give them exposure to, well, one, just by removing the material around them if they're trapped in an over-consolidated state, or if you also give them access to air and or water, they may tend to start swelling. I don't necessarily have a lot of experience with it, but I know that it's a condition that's at issue, and we certainly often in the geotechnical investigation will ask for swell potential tests to be run on the material. These are lab tests that you can run on samples of the rock, or you run them in the borehole while the bore is being done, to get a sense of what the swell pressures might be. Again, the contractor needs to know that. If they're designing the tunnel liner, a fixed type of tunnel liner, and there's going to be more than just normal vertical overburden loads, but if you're going to have swelling loads on top of that, then the contractor needs to know that to design the lining. And if you're considering pipe jacking and you know that you're in a squeezing or a swelling material, even if it's rock, that's going to impact the jacking forces of that tunnel. And depending on the magnitude of the potential swelling, I mean, it could be to the point where you really don't want to consider jacking, because you're going to have so much increased load on that tunnel that you're at jeopardy of not being able to finish the drive before you've locked the tunnel in place.
Okay.
So in the parts of the country where those conditions can exist, it's certainly an important consideration to characterize and understand.
Right. I think we may have time to tackle one more question, and then we'll hand it over to Carrie for some final comments and wrap up. But Nathan, I saw you answered one of the questions about production rate, and maybe not everyone got to see that. You want to talk a little bit about production rate on your SAWS project?
Yes, so with this project having 10,000 feet of tunnel, it was critical that production rate moved at a pace to make sure the tunnel would be completed within the time frame for the project. The contractor brought on 9 crews, and they kind of rotated around different areas and had multiple tunnels progressing simultaneously. So what we were seeing was about 3 to 5 feet per shift per day, so anywhere between 9 and 15 feet. Just kind of depends on the time of day, the softness that they encountered. But based on the size of diameter and what they were able to move, that was what was being progressed. So, and in some instances, they even tunneled in 2 directions. So making sure that they were true in line and on grade, and when you meet in the middle, not having any issues is critical. But the contractor was very efficient and well-versed in handling tunneling operations in this area.
Great. Well, with that, I think I'll pass it back to Carrie.
Perfect, thank you. Let me share my screen for y'all real quick. First and foremost, thank you to all of our presenters, and then to all of you just for your attendance today. I hope that you found the webinar informative and have things to take back to your colleagues and your own projects moving forward. You will all be receiving an email from myself following this event with a link to our post-event survey. I really do ask that you just take a moment to fill that out. That is how we can just continue to make these webinars better for you in the future, and we always love that feedback. And as always, if you have any questions, please do not hesitate to contact NASTT, whether it is other educational offerings, coming to our show, getting you in touch with somebody who can help. We would be more than happy to just get you going where you need to go. But again, thank you all so much, and I hope you all have a wonderful day.